Hey guys, so today we're looking at experimental designs. Um, Experiments are if you can properly set them up, if you can, uh, you know, go through the actual proper protocol of the experiment, collect data, replicate it. This is the best research method in terms of showing actual cause and effect. Because an experiment is the only type of research method that truly isolates that one variable. Okay, you are manipulating only the independent variable and then getting your dependent variable from that, which is kind of like the data you're collecting. So if you're not isolating a single variable, if you have like two variables that you're changing, it's not an experiment. It's not cause and effect, because if you're manipulating two variables, well, is it this one that's causing the change in the dependent variable, or is it this one? You can't know. So if you set up a good experiment, you only have your one independent variable. Um, that's the only thing you're changing. That's basically the only thing that could be explaining, if you see a difference in the dependent variable, what's causing that. So you have your hypothesis, which is where you set up your question that you're trying to find. You have your statement in relation to two or more variables. It must be testable. Okay, make sure it has good operational definitions in it, so you know exactly what you're looking for, and people trying to replicate this know exactly what you were looking for, so they can replicate it exactly as you did it. And instead of trying to prove a hypothesis, science usually tries to disprove a null hypothesis. Okay, so a null hypothesis is the opposite of your hypothesis, and it's indicated by this little zero subscript here. So your examples is gender has an effect on spatial ability. Your null hypothesis, which you're trying to disprove, is gender does not have an effect on spatial ability. Okay, and this is not a very good operational definition, so you would need some sort of a explanation of exactly how you're testing spatial ability. Um, So, like, gender does not have an effect on the ability to solve, this puzzle in under 3 minutes, or something like that. Or all genders will be able to solve this in under, this puzzle in under 3 minutes. So, and also statistical significance. So, statistical significance only tells us that the findings are probably not due to chance. Okay, so that you're not looking for, like this proved or disproved my null hypothesis, or like that's significant, or like there's a big change. Statistical significance only like this data is actually testing what I want it to test, or this data I got from the experiment actually, getting the information that I wanted to, not by chance, but because of the manipulation of the independent variable. That's what's causing this change in data, if there is one. So you got your variables, super important. Okay, you have your independent variable. That is what you were changing. Time of day on test scores. I'm controlling the time of day. That's what I'm manipulating. Okay. The temperature of the room when kids are taking a test. I'm controlling the temperature. Is it 65 degrees, and then another group of students is taking when it's 80 degrees. Okay, and then my dependent variable is the data I'm getting that's influenced by the change in the independent variable. So it'd be the test scores. And those examples. So that's the data that you're getting is the dependent variable, and then everything else is confounding or extraneous variables that you need to really make sure that they're constant and they're not interfering with the independent variable. If I have a class, I want to test the effective temperature of a classroom on student performance. and I do my good operational definition, so I know exactly what the temperature is and exactly what type of test data I'm looking for. But if I do my 65 degree, classroom temperature and my 80 degree classroom temperature, but this classroom is different than this, maybe this is like a darker color to it, the lighting isn't as good, or there's more colorful things on the walls that might be distracting to students, or so you gotta be like, same classroom, same distance apart from desks of students, try to keep everything else the exact same, so the only thing you're manipulating is that independent variable, so you know for sure that the dependent. And that's why we do, one of the reasons why we test things over and over and over again, because someone might say like, hey, I got this, like I got all these good data, and then someone else does the exact same experiment down the road. It's like, I got different data. What's going on? Well, how did you set up this? And then maybe one of those confounding variables actually were changing things. They didn't realize it. So that's why we have to do it multiple times before it's like, yeah, it's the exact same results every time. We got this. We got the good, independent variable. We're not messing up with extraneous variables. We're good. Control group. Okay, so this is what receives no truement. This is your baseline, and this is for the basis of comparison. And then you have your experimental group, which is the one that you are changing the the variable on to see what data you get. So you have your different control measures, counterbalance. So doing things in like a different order. To make sure that's not just the order of events that are manipulating the the data that you're getting. So if you remember the ash line experiment, where you have the lines that they were given to the different different people, to see if they like agreed with they were the same length and stuff, and the people were like, no, that's clearly wrong, but they're saying yes, but the person's like, oh, they said it was yes, I must say yes too. So like using like the order of the lines, like mixing them up, just to make sure they're not doing it just because the order of the cards that you're presenting, but truly based on the independent variable of where they are in the line of the subjects there, saying whether they thought line A or line B were the same lengths or not. So kind of mixing up the order of cards, that would be counterbalance. Single blind is the subject is unaware of whether they're basically in the control group or the experimental group. If you remember the one video we watched on the professor studying alcohol and the effects of alcohol and stuff, and all those research students, she was like giving them beer and stuff, and they're like, oh yeah, this is great, and he's like, oh yeah, by the way, like half of you got non-alcoholic beer, and like a lot of you that are acting like you're drunk right now aren't really drunk, but they didn't know. They had no idea that some people were getting non-alcoholic and some people were getting regular beer. Double blind is one step further, where neither the subject or the experimenter knows. So you're testing a new medication. You have, the pill, and you have a placebo, which is like a sugar pill, which isn't actually the medication you're giving them. The subject doesn't know whether the pill they're getting is the real one or the placebo, and the researcher, the one who's giving them out, also doesn't know which is which. That is being controlled by a level above them, and they just give subject A this, and they don't know whether it's the. So that helps to try to avoid bias. And then randomization from your population and from your sample. So you have the population is the group of people, the large group that you draw a sample from, and the sample is the representative group of that population. Okay, so you can't do your research method on like a huge group of like a whole population. So you pick a representative sample of that. okay, to try to get your accurate data that represents an entire whole. And there's two ways that you can get a sample. One is random assignment, where you have your population of 100 people, and you assign all of them a number, and you put it in a big fishbowl, and you draw out 15 names, or 15 numbers. And you don't know who they are, who they correlate to. You just like bam, 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 bam. And so every single person in the population has an equal chance to be drawn. Or you have a stratified. Okay, so you look at your population and you break it up into some sort of representative groups. So you could do it by ethnicity, you could do it by gender. It kind of depends on what you're studying. So, I'm trying to, I do an overall kind of like a Mesa High population. So I pick a certain number of, what percentage of Mesa High are seniors, what percentage of Mesa High are juniors and sophomores and freshmen. And so I pick, based on that percentage, this number of freshmen, this number of sophomores, this number of juniors, this number of seniors, to now have my research method or whatever I'm doing, maybe a survey or something, but they're the ones going to be filling it out, because even though it's not everyone, those 4 freshmen and 5 sophomores and 5 juniors and 6 seniors or whatever represent the population as a whole. So that's our experiments. Only type of research method that truly shows cause and effect, that shows causation, not just correlation, and preferably the best type of research method you can do, but not always applicable. But if you are doing an experiment, super important to make sure that you're doing it correctly and you're only manipulating that independent variable. Otherwise, it can skew the data and not get you the findings that you thought you were getting.